Section 4.1 is about divisibility. And in this section, we're going to take a look at how you can more easily decide if a number will divide evenly by another number. In particular, I know you guys have your phones with you a lot, maybe like 24/7, maybe they're attached to your hand, I don't know. But you should be able to look at a number without a calculator and decide if it's divisible by certain numbers. And that's what this section is really about. It's kind of a mental way of checking for many numbers, not all, if they're divisible by certain values. So the first thing we're going to look at is what the definition of the word divide means. So if A and D are whole numbers, we say that D divides A. It's written with this vertical bar between it. Be really careful. It's not like a fraction where the number on the left side is on the top and the number on the right side is on the bottom. That is not what it says. It's read D divides A. Right, so that vertical bar is read as the word divides. If and only if there is a unique whole number Q such that A equals DQ. If D divides A, then D is a factor of A or a divisor of A. And sort of the reverse description is that we can say that A is a multiple of D. So we'll use those words a lot. So let me just do a real quick easy one so you can see how this plays out definitionally. We would say that 2 divides 10. That's how we would write it. And the reason is because 10 is equal to 2 times something. What is 10 equal to 2 times? 5. So this is the Q that they're referencing above. There is a number that you can multiply by the divisor, the 2, to get back to the original 10. Okay, so if we used this example, we would say that 2 is a divisor of 10. That's one way we can say it. We can say that 2 is a factor of 10. Or a third equal way of saying this is that we can actually say it flipped around to say that 10 is a multiple of 2. All those statements mean exactly the same thing. They're just stated in a slightly different way. So Theorem 4.1 follows next, and it says for any whole numbers A and D, if D divides A, all right, so this is something like 2 divides 10, and N is any whole number, then D will divide N times A. So again, this isn't proving it, but just using that same 10 and 2 that we said before. 2 divides 10, check, right, like it works. Then that means 2 will divide 10 times anything you'd like. 10 times 5, 10 times 7, 10 times 9, 10 times 2,467, right? It will have to divide it because 2 divided 10 to start with. Okay? So that's this particular theorem. And then we're going to look at Theorem 4.2, and I'm going to write these ones out, I think. I think they're all blanks. There's 5 different theorems. Some of them kind of go naturally together, and we'll see that as we go. So again, we're looking at the numbers A, B, and D, and we're looking at divisors. So if D divides A and D divides B, okay, so 2 divides 10, 2 divides 6, whatever. A number divides 2 different numbers. Then D will divide A plus B. So again, thinking 2 divides 10, yes. 2 divides 6, yes. Well, 2 is going to divide 16 as well, 10 plus 6. And it works all the time. There's nothing special about my 2, my 10, and my 6. That's always a true statement. And sort of the flip of this one goes along with it. If D divides A, but D does not divide B, okay? We like to put these little slashes through things when they're not equal, right? This is the same thing here. This does not divide. So if D divides A, but it does not divide B, then it won't divide their sum. And D will not divide A plus B. So again, 2 divides 10. Cool. 2 does not divide 5, right? No, 2 does not divide 5, so 2 is not going to divide 10 plus 5 or 15 either. And again, not unique to those numbers, it always works that way. Now what you will not see me writing next is what happens if it does not divide A or B. Okay, so notice in these two, at least this part's the same, right? I'm not going to have a third statement that says, okay, well, let's destroy it one step further. We're going to not divide both of them and see what happens. And the reason that we're not is because it can actually go either direction. You could have two numbers that are both divisible, not divisible by D, but then their sum is, right? So think about odd numbers, right? So like 2 doesn't divide 3, 2 doesn't divide 5, but 3 plus 5 is 8, and 2 divides 8, right? But let me change it up a little bit. We'll do 3s. 3 does not divide 1. 3 does not divide 7. 7 plus 1 is 8. 3 doesn't divide 8 either, right? So it could continue to fail or it could actually succeed. It just depends on the actual combination of the values you use. So we don't have a theorem that talks about that because it can go either direction. We still have a couple more though in this one. So if we have D divides A and D divides B, so back of the same as like the first part, our other condition is that A is going to be bigger than B. Not because it matters, but one of them's bigger. So we're just pretending that it's the A value. Doesn't matter. But what we're going to see then is then D will divide the subtraction. So D divides A minus B. So whatever the value is that's bigger, minus the smaller one, because we are still working with whole numbers. We are still in the whole number system in all of Chapter 4. When we get to Chapter 5, we'll expand our universe a little bit, but right now we're still working whole numbers. So we get our whole number system. We still want to talk about whole number division. So again, 2 divides 10, 2 divides 6. 2 is going to divide the subtraction of 10 minus 6. 2 divides 4, right? So it's going to work. And it's going to fail exactly the same way the second step failed if D does divide A, but D does not divide B. And again, we've got A greater than or equal to B just so that we can make sense of having a positive number. But D will not divide A minus B.
What is the A greater than or less than, I mean, greater than or equal to B? I know that's not greater than or equal to.
Yeah,
What is that symbol?
it's actually, it's a greater than or equal to symbol.
Oh.
Yeah, it is. And it's just specifying for us that we're going to take the larger value minus the smaller value. So that's why you're seeing the first letter showing up here, A.
Okay.
It's just so that you still get a whole number. That's all we're trying to ensure is that we have a whole number we're talking about for this division, since we've only worked with the whole numbers so far. There's another one here that gets thrown in, and it's really just the same as this one. These two are the same, okay? So let me talk about what happens if D does not divide A, but D does divide B. So A is still greater than or equal to B. It's going to follow, again, that D does not divide A minus B. Now, I'm saying these two are the same. I mean, they're not exactly the same, but they're quite similar, right? It doesn't divide one, it does divide the other. I subtract, and it's not going to work. The reason I don't have that happening up here is because addition works either way, right? I didn't have that extra condition that A is greater than or equal to B to contend with to make sure that I'm really getting numbers that are really whole numbers. So that's why it's written in two steps, not because there's really two different things going on, but because we've got the subtraction going on, and subtraction has an order to it, right? A minus B and B minus A are not the same thing. We end up getting this sort of a two-part thing at the bottom that are just a little bit interchangeable in terms of the values being used. We're going to come back to a lot of questions with this later. Yeah, Jenna.
If A and B are equal, wouldn't that be 0?
Yeah, it would. And it actually holds for that too, because any number will divide 0. It's kind of a default kind of thing. It sort of seems like a silly question, but right, 0 divides by 5 just fine. It's still 0. So it would hold if it was equal as well. That's why it says the equal to, and it works. Yes.
I was trying to be like, it divides 0, not like it
Oh, divided by 0. Yeah, we don't get that part of it. You're right. Okay, so what we're going to do next is we're going to look at some divisibility by some very specific values. We will come back to this Theorem 4.2 with some examples on them specifically and how they kind of interplay with each other, but it may not be this class period. That may actually be Wednesday. But I want to look at some very specific values with you and think about your divisibility tests. Now, some of them you probably know, and some of them you probably don't. Let me not put my screen up just yet. The ones on this page that we're looking at right now are 2, 5, and 10. So how is it that you know, looking at a number, if a number is divisible by 2?
If it's even.
If it's even. What does it mean for it to be even? Don't tell me it divides by 2.
It jumps 2. Starting at 0 and 2. It adds 2.
Okay, so that's a recursive kind of a description, Emily. You're not wrong, but when you're looking at the number, how do you look at the number and say even? All the numbers have a partner. That's how you would divide them apart. But how do you just look at a number and know that it's even? What do you memorize? It's memorization. What do you mean by memorization? Okay, with counting by twos is this recursive idea. So I don't think you want me to give you like 4,276 and you to count by twos up to see if you're going to get there, right? Oh, okay. You look at the what? The last digit. It's all about that last digit, isn't it? And what has to be true about the last digit? It has to be even. And an even last digit would be the digits 2, 0, 2, 4, 6, and 8. Yeah. Okay, so that's our divisibility rule for 2. So we're going to write it in just a second. These are grouped together for a reason. What about 5? How do you know if something's divisible by 5?
It ends in 5 or 0.
Abby's like, I'm cutting to the chase this time. It's how it ends, right? It ends in a 5 or a 0. Okay, so the divisibility rule for 2s and 5s are exactly the same. And what do you think about the divisibility rule for 10? It ends in a 0. So these 3 get grouped together because it's all about the ending digit. And not all of our rules have this sort of a property to them. It's just these 3. Okay, so I can't do this with the divisibility for 3s. I can't look at the last digit and just know. I can't do this for divisibility by 8. I can't look at the last digit and just know. But I can do it for 2s, 5s, and 10s. And I expanded this a little bit further. We talked about this being divisible by 0, 2, 4, 6, or 8 as our last digit. Okay, so 2, 5, and 10 are alike. As you flip your page, you've got a whole long list of some more of them. The next 2 that are alike are the 4 and the 8 rules. Okay? These you might not know. They aren't ones that are often talked about quite as frequently, at least as not as frequently as the 3 that we just talked about. We'll do 4 first. How do you know if a number is divisible by 4? Has anybody seen that one before? Okay, if it ends in a 4 or an 8, it is divisible by 4, maybe. Okay, so it certainly would have to be divisible by 2, but is that enough? It has to be divisible by 2 twice. That's true. But can you tell just by looking if something's divisible by 2 twice? If it's a small enough number, you probably could, right? Bigger numbers, maybe not. So our divisibility rule for 4 is actually kind of interesting. It actually does involve looking at the last digit, but it's not just the last digit. It's the last 2 digits. So if the last 2 digits, as a 2-digit number, are divisible by 4, then the entire number, no matter how long or ugly or whatever it is also divisible by 4. So Abby speculated that maybe ending in a 4 or an 8 would work. And it does sometimes, right? So like if the last 2 digits were 28, right? 2, 8, is 28 divisible by 4? Yes. So no matter what came before it, all of that combined put together would be divisible by 4 as well. But if it were like 18, is 18 divisible by 4? No. 18 is not divisible by 4. So no matter what came before it, if it ends in 1, 8, it will not be divisible by 4. 8 is similar. So you divide by 2, looking at only the last digit. To do divisibility by 4, you have to look at the last 2 digits. To do divisibility by 8, you have to look at the last 3 digits. Okay? And again, you look at it as a 3-digit number. You just take the last 3 digits and you say, hey, look, there's 3 digits. Do those 3 digits, if I divide by 8, divide? And if they do, the entire number previous to that, combined with those last 3 digits, will also divide by 8. The divisibility by 8 is probably not as useful in general as the others. And the reason is because you probably looking at a last 3 digits of a number don't know necessarily if it's divisible by 8. Agreed? You might be able to do it with the last 2 digits and decide it's divisible by 4, though. You might be able to do that if the number's small enough, right? If the number's like 94, you might be stuck. But if the number's like 64, you might stand a chance, right? If smaller numbers compared to a bigger number. But 3-digit numbers are very difficult. However, if you were still using this and you weren't using a calculator especially, right? That calculator kind of makes this seem a little bit unnecessary if you're utilizing it. But for the most part, the ages of the kids you guys are going to be teaching, they're not using calculators. Agreed? Probably not. My 7th graders are still not using calculators in their schools right now, at least not on an everyday kind of basis. They're still working with things that their teacher wants them to be able to do by hand. So most of the kids you guys are working with are not going to have a calculator at their disposal like you guys do, and I get that. And I hope you think about that as you're doing it too, because I know that sometimes you're going to get frustrated. You're going to be like, but I can just do it in the calculator. Okay, but your 3rd grader, right, is not going to do that. Your 5th grader is not going to do that. So what are they going to do instead? So the reason that this can still be a useful one, even though it's not quite as user-friendly, is that it's still easier to take the last 3 digits of a long number to see if it divides by 8 before you go through all the effort to try the whole number divided by 8. Right? If you had a 6 or 7-digit number and you want to know, is it divisible by 8? Should I even try? Well, you might take the last 3 digits and do a quick division of that instead first before you go through the efforts in case it doesn't work. Especially if you get into what we're doing later in this chapter, which is factoring things, which is a upper elementary, lower middle school process. So that you're aware. Okay, so this is divisible by 4 and 8. The next 2 go together, 3 and 9. Has anybody seen divisibility by 3 before? Maybe?
If the numbers are added up and they're divisible by 3.
Yeah, so I remember when I first learned divisibility 3 by 3, and it was one of those things like those aha moments where when the teacher said it, I was like, are you kidding me? And nobody ever told me this. So this might be your aha moment day. So you take all the numbers, 6, 7-digit number, whatever you have, it doesn't matter. It works for small numbers too. You add all their digits together, and it's divisible by 3. Then the original number is divisible by 3. So let's take a really simple example first, something that you already know. 27. It's just a 2-digit number. You should know it's divisible by 3. But check it out. What's 2 plus 7?
9.
9. Is 9 divisible by 3? Yes. Therefore, 27 will be as well. And it works for all 3-digit or all divisibility by 3s. But here's the cool thing. That exact same rule works for 9s. Add all the digits together and it divides by 9. Then the original number divides by 9. And in fact, you probably knew some version of this along the way when you learned your multiplication by 9s tables. Right? Think about your multiplication table of 9s. 18, 27, right? You guys know what I'm talking about, right? All these numbers. All the 2-digit numbers that you remember from those multiplication tables add to 9. Every single one of them. Like exactly 9. 81, 72, 54. Every single one of them, they add to 9. Right? They do. So that's actually true for longer than just 2-digit numbers, but that's a property for 9s. Sorry, I should have switched the screen. I apologize. So when we're looking for divisibility by 3s or 9s, we're doing the same thing. We're adding all the digits together, and then we're testing whether that sum divides by 3 or that sum divides by 9. And typically when we add all the digits together, the sum is something that's small and easy to work with. It's something that you already know whether it divides by 3 from your multiplication tables, or you already know if it divides by 9. We don't sum things together and get a 3-digit number. It doesn't happen. We're not working with numbers that big, okay? All right, Theorem 410, divisibility test for 11 is the absolute most difficult test to write down. So I'm going to just show it to you here in a second, but then I promise I will give you an example so you can see how easy it is to work with. There's just not an easy way to write it down, okay? We'll talk about 6 in a second. A whole number is divisible by 11 if and only if the sum of the digits in the places of even powers of 10 minus the sum of the digits in the place of odd powers of 10 is divisible by 11. And I don't know of any better way to write it than that. That's saying something because that looks awful, doesn't it? It's really wordy. It sounds really confusing. I'm just going to make one up and we'll see what happens. I'll write it up here in this purple part. These are random numbers. I just made them up. There's nothing special about this. What this is telling you to do is to take every other digit and add them up. So 3 plus 2 plus 1 plus 4. I think I got 10. Is that okay? And then we're going to do the same thing with the digits that we didn't already add up. 4, 6, 8, and 9. And I have 27. Sorry, that blue was not the best choice. Let's try that instead at least. Okay, so when it's talking about the even powers of 10 and the odd powers of 10, it's just talking about the placeholders, right? So like the 9, where the 9 is located, is 10 to the power of 0. The 4 is 10 to the power of 1, right? As we move over, remember doing our powers of the base. That's what it's talking about in those evens and odds in that description. So we're taking the sum, and then we're actually subtracting them. And it doesn't matter which way we subtract. It's just big minus small. So 27 minus 10 is 17. Okay, everybody good? You got 17? Is 17 divisible by 11? No. Then it means that that original number with all my circles around it also would not divide by 11. Okay, so we take 27 minus 10, we get 17. 11 does not divide 17. So 11 will not divide, heavens to Betsy, 3, 4, 2, 6, 18, 49. So it's not a hard rule to sort of do. It's just not convenient to write down. 411 is very interesting. 411 says, a whole number is divisible by 6 if and only if it's divisible by both 2 and 3. And it seems quite reasonable, doesn't it? That seems reasonable. I don't think I even have to utter why it seems reasonable. Just, right, 6 is 2 times 3. That seems to make sense that it would work like that. There's actually a bit more hiding behind that than just what's written there. So I'd like for you to get into groups. I know this feels like we're running in a little bit different order than normal. We're going to explore a little bit about this divisibility rule by 6. So I don't know that I care necessarily where you are. So if you just want to like group up in 2s or 3s where you're sitting, just so that you don't have to move too far away, that'd be great. So shift your desks together. You're going to have to talk. Because what I'm going to do is I'm going to write some stuff on the screen about divisibility. Okay. So the reality is this divisibility rule by 6 business can be generalized. But there are cases where it works like this, and there are cases where it doesn't. So what I'm going to do is I'm going to create for you a list of examples and non-examples of when it works and when it doesn't. What your goal, quietly in your group so that you don't spoil it for anybody around you who's not in your group, what your goal is to figure out what the examples have in common and what cases that they don't, so that you can figure out when this rule works in general and when it doesn't. Okay, so if a number is divisible by 6, it means it's divisible by 2 and 3. If it's divisible by 2 and 3, it's automatically divisible by 6. That's what that divisibility rule said, right? Okay, so we're going to do some examples, and the first one is exactly that one that I said. If it's divisible by 2 divides 3, I didn't say that right. I'm going to write it this way. If it's divisible by 2 and 3, it's automatically divisible by 6. Okay? So I'm going to give you some more. It's divisible by 3, wow, and 5. It's automatically divisible by 15. If it's divisible by 2, let's do 3 and 8, then it's automatically divisible by 24. Okay? So, some non-examples. If it's divisible by 2 and 4, it does not always divide by 8. If it's divisible by 3 and 12, it does not always divide by 36. If it's divisible by 4 and 6, it is not always divisible by 24. Okay, so I'm going to stop right there, and I'm going to let you guys talk. Your goal is to try to figure out what the things on the left have in common that the things in the right fail to have in common. To see if you can figure out what it is that makes the ones on the left work while the ones on the right fail. And once you decide in your group that you think you have it, get my attention. I'm going to come over there and I will let you know if you have it or not. But if you have it, what you have to do is not tell everybody in the class, but to provide either an example or a non-example to add to my list. Are you following? Okay, so your first rule, the first thing you're going to do is to try to figure out what is it making the numbers on the left work and what's making the numbers on the right fail. Okay? have that one up there. You guys are noticing some very interesting things, so I'm adding things to the list so that they destroy what you thought was true. Yeah, that's the goal. Destroy all the happiness. Is that 98? Yeah.
It sounded like it felt good. It sounded like it too. Such a fast crowd. She's holding up the surrender flag. Oh my goodness. Can we get a clue?
There's a whole board full of clues.
Those are good clues.
Yeah, can we get a clue, like not an example? Phone a friend?
Phone a
Or
friend.
just like a hint, that's not like an example.
Okay, so your hint, I hear a lot of questions asking about what happens with the products. You're using the word sums, but you mean products. Okay, these numbers have nothing to do with it. Okay, those have nothing to do with it. Your comparison needs to be looking at these numbers and how they each compare to one another, and how these compare to one another. I didn't hear what you said.
Was it a bunch
Check your You're on the right track. See you're saying most of them do this. They all do that. pattern, right? This is like a legit problem-solving strategy session. Pattern recognition. Sorry, it just was overwhelming on the board. There's too much going on. Do you guys have one for me? Mm-hmm. Yep, 3 and 4 would work. And then what about 3 and 7? No. 3 and 7 will work. Yeah, it does. 3 and what? 3 and 9 will work. You do that. Like it'll work on this list. Yep. Well, there's more because another group figured it out and they added to my list. We're trying to find for when the test for 6 generalizes.
Does this list go on and on and on? Like, is it infinite?
It is infinite. You betcha. We could do this all day. I mean, we're not going to, but we could. Okay, so Elizabeth, make your observation you made to me just out loud. See if it might spur some other thoughts that others have, because you have things on the right track, just not the why behind it yet.
On the example side, the factors will never be an even times an even.
And that's true. They won't. But why? You guys really want divisibility by 3 to be part of this. It's not, I promise.
Is it because if it's multiplied 2 even numbers together, then the answer will only be able to be divisible by at least one variable being even?
Didn't quite follow that, Emily. Sorry. Think about rewording. What do you think, Kaylee?
You can try to explain it.
Well, I would kind of disagree.
Well, that's okay, because I don't think I'm right. I just shot in the dark, you know?
I thought because if it's 2 evens, then they are only going to be divisible by an even.
Yeah.
But 6 is an even.
But yet, to be divisible by 6 has to be divided by 3 as
6
well.
is 2, 4, 6.
I know I said 6 is even.
Oh, basic isn't.
Yeah. So evens aren't only divisible by evens. That's true. They're not only divisible by evens, which I think was what Hallie was like saying in that particular description, right?
Well, you said the reason it would be wrong is because an even times an even equals an even, but 6 isn't even, so that doesn't really make sense. I was saying because it can't be 2 evens because of that.
Can't be divided by 6 because it has to be divided by 2 and 3. Something like that. Maybe not.
Yeah.
Man, another hint without giving something away.
Can I give it away? Do you have a hint that won't give it away?
Do you have a hint that won't give it away?
The biggest thing I got was like she gave you a lot when she was like compare the numbers themselves, not the product, the numbers.
Yeah.
And don't just like compare like one side, those two numbers together, compare them with the other side as well. Like some
So,
I don't know if I can
like-
say that.
So like compare 2 and 3 to 2 and 4?
Yes. What do
Yeah.
2 and 3 have or
2
not
and
have
4?
that 2 and 4 do? Or 3 and 5 that 3 and 12 don't? Or 3 and 8 that 4 and 6 don't? Or 4 and 9 that 6 and 9 don't?
We probably already said this, but every single one on the non-example has it. No, never mind.
They don't have to only have evens.
Yeah, 3 and 9 is not.
Yep, 3 and 9 is not even. And it still fails.
This is trying to make it.
When we add the numbers together.
No, don't add the numbers together.
Well, I'm a loss. I'm not a loss.
Okay, Jenna, you got the floor. Jenna's,
I got
does somebody else have one more idea?
I have a
Okay,
thought.
Gracie.
Well, like, 2, like, can go into 4, and 3 can go into 12. And 2 also can go into 4 and 6, and 3 can go into 6 and 9. None of that on the other side goes for it.
Okay, so that is on the right track, but can you make it generalized, Grace, maybe?
Isn't the difference between all the examples are prime numbers?
Ooh, that's a good guess. They're not all primes. They're close, but like 10 and 3 worked, right?
Like, the factor tree thing can't happen on the example side, but it can happen on the non-example side.
The factor tree thing.
That's a horrible name for it. I just don't know. I know what you're talking about.
The
Yeah,
little thing
like,
that comes down and then it comes down and then comes down.
yeah,
Like,
like
break
you
up.
couldn't
You can break
put,
them up. You could do that for 56.
for everything on the non-example side, you could make a factor tree from with the numbers staying in common for the bigger number.
I'm not sure what you're referring to about
But on
that.
24, you can do 3 and 8, and then 8 can still go into 2 and 4, and then 4 can go into 2 and 2.
24.
On the
That's
example.
not the way she was talking.
It's like Emily's so
Okay. We have exactly 1 minute left. So Jenna's got the floor because she asked for the floor. Do you want to tell them what it is?
Okay, so you guys were on to it with the factoring thing. So the non-example slides, you were right, 2 and 4, they have 2, 3, and 12, 3, but it doesn't have to be like a number that's in it. 4 and 6 are divided by, like, they have factors. All of them they have factors in common, but like 4 and 9, for example, on the example side, they have nothing in common.
That's what Chris was saying.
Yeah, that's
Okay.
That's
So,
what you were saying.
But you were saying it in sort of like these 2 categories kind of things, which is how you guys were starting it with it too when we were just talking about it initially. So all of my non-examples, every pair of non-examples have a factor in common. 2 and 4 both divide by 2. 3 and 12 divide by 3. 4 and 6 divide by 2. 6 and 9 divide by 3. 10 and 4 divide by 2. 4 and 8 divide by 4. 7 and 14 divide by 7. And 3 and 9 divide by 3.
Ah, son of a gun.
That does not happen on the other side. So what does that mean? It means that if you were asked to break down the number 24 into 2 numbers that you could test that were smaller, you can break it down into 8 and 3. You cannot break it down into 2 and 12.
I see it.
Do you see what I'm saying? If you take, I'm exampling the 24 because it's on the screen. If you take the 24, you can break it down into things you can test, just like 6. 6 breaks down into 2 and 3. You can test them, and it's easier to test the 2 and the 3 than it is to test 6. 24, easier to test 3 and 8 than it is to test 24. But you can't just break it down into just willy-nilly anything. It has to be broken down into things that have no factors in common.
Can I add
All right.
an example now?
Yes, you can add an example and then we'll end class. What example do you want to add?
2 and 2.
2 and 2. 2 and 2 would be a non-example though, because 2 and 2 have 2 in common. Good try. 2 and 2 would be over here. All right, we'll pick up next time where we left off.